Yes.
Okay, so good afternoon, good evening, everybody. So we are happy to listen to Yvain Bruned from University of Lorraine in Nancy about Novikov algebras and multi-indices in regularity structures. Please, it's yours.
Thank you, Dominique, for the introductions, and also to the organizer for this online seminar to give me the opportunity to talk. And today I will report on a recent work, joint work with Vladimir Dotsenko, where actually we explored the free structure of a combinatorial set, which has been used frequently for expanding solutions or for singular SPDs. So stochastic partial differential equations. And the idea was that decorated trees or trees have been used for expanding solutions since more like around like now maybe 10 years. And recently another combinatorial set has been proposed, which are multi-indices. And they are extensively used now in the context of Ricci structures for singular SPDs. And in this project, on this talk, I will show or present you that actually these objects are connected to Novikov algebras. So for instance, for trees, it is pretty algebras. For multi-indices would be Novikov algebras. So it's what I will present in this talk. So first, I will not directly present you the multi-indices in the context of SPDs or PDEs, partial differential equations, but rather the very simple one. I will start by the one that will face, for instance, in ordinary differential equations. So what are multi-indices? First, you fix a collections of variables, so this zk indexed by n. And if you want this zk, you could see them as some nodes of a tree, and k will correspond to the fertility or the arity of the node. So meaning that the tree has k children. And then a multi-index, so multi-indices over n, it's just given as a monomial, or if you want, a product of these variables zk. And beta will beta k just count the number of times the variable zk appears in your monomial. So that's the definitions of a multi-index. And then one can actually define on these multi-indices a derivations, which is given here below, where these derivations boils down to say that I will erase one zk, so one variable in my monomial, and I will replace it by a new one, which is z subscript k plus 1. So I increase the arity by 1. And then I have some combinatorial factor that I could consider here or not, depending on what is the convention you make for the definitions that tells you that in front of this derivation. So this is an infinite sum, but this is just for, you have derivatives toward this zk. And if you look at these derivations, capital D, you are able to define a pretty product between two multi-indices, which is defined by applying the derivations capital D on Z beta prime, and then you just multiply by Z beta. So that's the structure, the pretty structure that you have on the multi-indices. And then, of course, in the applications, also when you look at the free structures, you don't want to consider all multi-indices. There will be restrictions on the there will be restrictions actually on the combinatorial restrictions on the multi-indices, which is below what we call POP3, what we call populated multi-indices. So these conditions boils down to do some power counting on the beta k. So here you have a sum over k, and then you have 1 minus k times beta k. So what does that mean is that if you think of each node having one outgoing edges and k incoming edges, it's like if you start to play with these nodes and try to build up a tree, in the end you shouldn't get only one empty spot if you want the outgoing edges of the root. Then the rest should be connected to a node or connected to a leaf. So this tells you actually that that's an important condition that we want to keep, these populated conditions. So where actually you can find them in applications. For instance, if you think about ordinary differential equations in dimension one dimensions. So by one dimension, I mean here, okay, I just have y prime equal f of y, so very simple ODE. And I consider it's like taking value in R. So I have an initial value, why not belonging to R. And okay, for this talk, you just assume that your function f is smooth and you can take as much derivatives as you want. In fact, you can get a formal expansion of the solutions where I will get actually this a series over where I sum over some combinatorial objects, and these combinatorial objects will be here multi-indices. So these are populated multi-indices. So there are multi-indices satisfying the conditions that are presented in the previous slides. And here you will get some coefficients, which are these elementary differentials. And these elementary differentials are just transparent. So you just associate it, you just associate to zk the derivative of a, the ks derivative of f. And then you take the power of beta k. So just, if you want polynomial evaluations, you just send that k to this f ks derivative of f. Also, okay, then you need to choose correctly the alpha z beta, so these coefficients, such that actually this is an expansion. Also, this formalism could be used for numerical schemes. You may want to get not the exact expansion of the solutions, but an approximation. So the approximation could be by just truncated the sum, just taking a certain number of multi-indices, or could be also by tweaking this alpha z beta, and this normally should give you a group for your numerical scheme that you can choose. So for instance, traditionally, this is mostly used, for instance, not with multi-indices, but when you put trees, and this will give you the butcher group or the B series for encoding numerical schemes. So that's an application of this, or where these multi-indices appear naturally. It is when you want to index, if you want these expansions, with this elementary differential. So you want something which is free for these elementary differentials. In very high dimensions, it would be the trees for these elementary differentials. In dimension one, the trees are not free. I mean, these elementary differentials will collapse, so there could be relations among them. And then the correct combinatorial set for looking at these elementary differentials is actually the multi-indices. So that's for the analytical connections, or if you want applications. Now I just want to go back. So we know that we define a pre-product with these capital Ds, but we get actually a bit more structure. And the structure is called Novikov, which are Novikov algebras. So here, just present briefly the definition. So Novikov algebra, it is a vector space. So it would be equipped with a bilinear product. And it will satisfy the two sets of identities. So the first one, which actually correspond to freely. So that's the one you will get for the trees when you do the grafting of a tree onto another one. But you get actually another set of identities, which are actually where you commute, actually, in its identity, you can commute z and y. That's due to the property of the derivations, which instead of the grafting, is when I define the derivations, the thing which is on the left is not attached to the derivations. So there is no, so that's why you can actually permute things. These extra identities put a lot of more identities in your algebra, and that's really show the different nature between multi-indices and trees, because here you have a Novikov algebra. And also it corresponds to the intuition you can get if you look at these elementary differentials, that moving from higher dimension to dimension one, you introduce more extra identities, which is analytical identities, which are actually reflected in this one, this algebraic one, these extra identities that you have for Novikov algebras. And then, of course, natural questions would be, what is the free Novikov algebra? Or you can describe the free Novikov algebra. The free Preely algebra is known. These are rooted trees. And in fact, this free Novikov algebra, it was a bit, I would say in a sense, hidden, or this thing was a bit hidden in the literature. And this was conjecture by a conjecture, like Dominique Manchon make the link between these multi-indices that I presented and Novikov algebra. And in fact, it goes back to this nice paper from Julian Balbaev, Lofal in 2002, where actually, if you go through their notations, I mean, it's a bit different, and Lofal is a bit different, but it's quite transparent that actually the multi-indices and the populated conditions that are defined, we can find an equivalent in this paper from 2002. And in sense that actually the multi-indices, the Novikov algebra of populated indices is actually the free Novikov algebras with one generator. So that's, if you want, the theorem, which is quite transparent in the work of Julian Balbaev and Lofal. So that's a nice fact. So then when I look at my expansions for ODEs and also my numerical schemes, then I know that now that this is like free Novikov algebras, and that's a correct algebra structure that I need to consider for my expansions. But that was a bit the starting point of my thinking about these structures, is that you want actually to go a bit beyond. So in fact, by beyond, I mean to go from ordinary differential equations to partial differential equations, and to what is my interest, stochastic partial differential equations, where you want to find an equivalent of this free Novikov in this level. So if you want, this was the same journey that we did also from Prelly algebra for just root treat to multi-Prelly and kind of Prelly algebras that we used for singular SPDs. So it's now what I would try to present in the rest of the talk. Also, please don't hesitate to ask questions with the chat or to interrupt me. What is the original? So I think it was kind of. I'm not an expert on this on the history of Novikov algebra, but this has connections with analysis or PDEs to find these identities, because the second identity really boils to the fact that you are looking at derivatives. So I don't know. I think there are precise reference in the paper, but I don't have right now. But there are like precise analytical connections with this second identity. And in fact, I would say that the person who will discover multi-indices in the context of SPDs is Felix Otto and his group. And Felix Otto is a person working in PDEs. So I would say multi-indices are extremely natural, could be very natural for someone working in PDEs, like an analyst. More natural actually than treat. Okay. Okay, so then now I move to the singular SPD case. So just to put some framework, it would be also in one dimension. So if you want, here I consider an SPDs, which is taking value in R. So there will be no in RD, like for the OD case. And then I will have some differential operator, capital, this mathfrak L. Think about the Laplacians, or that's the most common differential operator used there. And then we have a specific way of describing the right-hand side. So for us, the right-hand side is a linear combinations of noise and non-linearities. So if you want, here I have a collection of noise, which is xi, and these are space-time noise. So it could be noise constant 1, could be space-time white noise. Normally, these are random distributions, but for the moment, you could think of smooth random functions. And in front of each noise, I have a non-linearity that depends on this bold face U, which is actually a collections, it's U, and also a collections of partial derivatives of U. Because we are working with a PDE here, so we may want to also have a right-hand side that depends on some partial derivatives of U. And normally, the order of these partial derivatives should be smaller than the operator that you see on the left. And yeah, so you have a finite set of noise. And then what we can do is that we can consider certain variables. So this, which are the variables in this boldface U. And these variables will be indexed by some n in n d plus 1. So d plus 1, why? Because you have d dimension in space and one for the time. And then if you want this variable un, they encode like partial derivatives in u. So according to the different directions, so x naught will be for the time, and then you have all the other partial derivatives. And then, okay, we renormalize by some factorials. That will be give you, if you want, some kind of Taylor coefficients when you expand your solutions. And so when you do the expansion of solutions, what you have to do, you have to deal with this, which are written below, which are these elementary differentials, where actually here I'm computing a product where I'm taking derivatives on some non-linearity. So I have selected the non-linearity with L, and then I apply a bunch of derivatives on the variable un, and this will be to the power beta ln. So that's the number of derivatives that partial derivatives you apply on A. So if you want, this will be product of these would be, if you want, your new elementary differentials. So you need to take into account now that you don't have only one variable. So before in ODEs, we just get one variable, which will be this y, where you take f of y, so you take derivatives according to y. Here, you need to take derivatives according to all these variables, u, and these variables, which are partial derivatives of u. So if you want, you have a larger set of elementary, you have more elementary differentials. Okay, so then we move to something I call general multi-index. So this is slightly more complex to what we have seen before, but it actually is based on the same idea. So what happened is that I have on my variables, I have two components. So I have the first component, which is actually selecting the noise. So because this will be a selections on my non-linearities. For instance, when I will try to replace this variable by a non-linearity, I know exactly the one that I have to select. Then there is a second variable, which is w. And this is actually a word on the monoid generated as letters by the letters are from the alphabet n to the power d plus 1. So this corresponds, if you want, to this variable, u to the power n. So if I have n is a letter, it will be u to the power n. And then the multi-index will be just a big product over variables, which are depending on ZL and some words W in this monoid. And then I got some power beta LW. And for, of course, beta is like a finite support. So this product is just a finite product. Just give me a monoblocks. So in fact, we introduced with Pablo Linares this kind of generalized multi-indices in this way. So by looking, this was introduced in this way. So then when I make the derivations on these variables, the way I can encode it is that I will add a letter to my word. So for instance, if I apply dn, I will remove a variable which is z, matfrak l, and w, and I just add the letter n here to the word. So here it's commutative, so it doesn't matter. I mean, I put the letter n on the leftmost locations, but it is the letters are commutative, so there is no order. We get also a combinatorial factor, and this wn is just the number of times the letter n appears inside the word w. So it's really mimicking and just extending the definition we saw for the ODE case. And then what happened that instead of having only one product, which will be only one derivations, because I have a collections of derivations, I have to index my pretty product with these letters, which are these bold n in n to the power d plus 1. And when I compute the product, I just apply the beta derivatives of dn applied to the beta prime. So this is the exact definitions, but I need to specify which derivations I will select. Below, you have also populated conditions, where now because you don't know the k, before we were relying on k, which was if you want zk. Here it is replaced by the absolute value of w, which is the length of the word, meaning how many letters I have in my word. But otherwise, the populated condition is the same. Okay, so that's we say generalizations of what we've seen before. No, it's not the directions. Yes. So then, because we work with these different derivations, which are indexed by the letters, we need to enlarge or to extend the notion of Novikov algebra. And that is the notion that we introduced with Vladimir Dotsenko of multi-Novikov, which is quite inspired from what people are using as multi-pre. So in fact, it is an algebra which is equipped with some bilinear products, which are indexed by an alphabet capital A. And then you have a collections of relations, which are mainly you take the relations that you have from Preli and also the extra one that give you Novikov. You put, you label them, so you put these decorations on the operators. And then you need to be careful, just not to repeat yourself in these identities, but you get a bit more extra identities. If you want, there's 3 identities you need to have when you put the decorations. And then you have a nice result. Is that you can define this free multi-Novikov algebra will be given by these multi-indices, populated multi-indices that I've defined. And now you don't have only one generator, we have a generating set, which are actually the noise. Because remember that all the variables are first indexed by the noise and then by these words. So you have a new notion of free multi-Novikov algebras. And so the way the proof works, it's quite tedious, but it's exactly in the same way as the proof for Jumal-Dabael and Lofal for just Novikov algebra. Just go through the main step of the proof. You just extended them by using these extra decorations. And this allows you to repeat the proof. So then we are able to characterize the notion of this, what is a free multi-Novikov at the level of SPDs.
Yvain, sorry, what is the set A in this setting here?
The set A is n to the power d plus 1. These are the letters.
Okay, thank you.
Yes, just presented before. Sorry, I mean, there's an issue with this. Yes. Yes, it will be the letters. So here, if you want, I index it by n with this n belonging to n to the power d plus 1. You may think that's an infinite set. I mean, in practice, when you look at an SPDs like this, you do not depend on an infinite number of derivatives. No? The number, I mean, in fact, we have a fixed number of derivatives there. At the ball face U, it's just a finite number of variables. Okay, so then I move to the next slide. It says no more questions. Okay. But in fact, the results I presented is relatively nice. It gives us an understanding of what you need to do when you take derivatives according to these variables, so U and its partial derivatives. But in fact, when we look at SPD, we want also localized expansions and around the points. That's important for expansions. And we need to consider other derivatives, meaning that not only this capital D, but other derivatives. And for instance, by other derivatives, I mean the one which actually appear when you write a PDE, which are the partial derivatives in the different directions. For instance, this partial xi, which would be just these directional derivatives. And in fact, you have a nice, if you use the chain rule, in fact, you apply this partial derivative xi to, for instance, to one of the un, so it's like some of the u with some partial derivatives. You have some kind of a chain rule, so which is some identities which is given below. So for instance, I can erase one u to the power n, which have all these partial derivatives, and meaning that I do a shift on this n by adding one more in these directions ei. So here is the element of in the canonical basis of n to the power d plus 1. And okay, then also I have a combinatorial factor. So that if you want, it's just a pure analytical identity. I mean, if you just act with this partial derivative, I just got this identity. And then, okay, so now I have two sets of derivatives, if you want. I have derivatives like these partial derivatives, and I also have the derivatives in the u, the solution u, and also the other variables. So then I can try to see if they commute, or what are the relations that you obtain. Okay, so the partial derivatives, they commute. That's a fact. If you take two variables which are different, for instance, if you take u or partial x of u, and you take derivatives according to the two variables, this is a commute, of course. So there is no, I mean, it's kind of, it's quite nice. But if you try to apply first a derivative in terms of u, and then a derivative in terms of x, directional derivatives, they do not commute. So you have some correction terms. And this correction terms is not random. I mean, it's kind of precise. And it is also expressed as a derivative. So for instance, you get the derivative according to u when it's n, where you remove one direction. So you have you remove one shift. So in fact, here you have some kind of I mean, if you just consider the Lie algebra of these derivations, you can compute the Lie bracket. It is the bracket is trivial, but when you have cross derivatives, it's not trivial. I mean, you have some correction terms that you can compute, and this correction terms is actually a derivative, so you stay in the same space. So that's a nice analytical fact. I mean, it's just from the computations. There is no thing, but this is something very important. In that, if you manipulate elementary differentials or expansions in PDEs or SPDEs that use both of these derivatives, and if you want to use a combinatorial set or some algebra structures, they should reflect facts that these derivatives do not commute. So if you are blind to that, you are missing a key part of the structure. So that's very important. And to be honest, in the context of SPDEs, it took us quite a lot of time to realize that this was actually a central identity in our context, that this fact that these derivatives do not commute. So then we can actually abstract that, because what we want is that we want to keep these D derivatives, capital D derivatives that correspond to this partial UN. And we want to add also this derivative, these directional derivatives. And so then we need to, instead of considering words where the letters commute, we need to consider words whose letter will not commute, in the sense that we will have some quotiented by some relations that reflect exactly that these derivatives are not commuting. So for instance, I will just put letters, which are this di, which correspond to these partial derivatives. These letters di and dj will commute. The same for the letters which are belonging to n to the power d plus 1, n and m will commute. And then when I have a letter di and the letter n, they do not commute. In fact, I have the relations that are written, the analytical relations that I have on my derivatives. So now I want to work with these words whose letter you can check some relations. Yes. So that's the set I consider now. So this is a set of formal variables. So I still have mathfrak L that correspond to the noises for selecting the correct nonlinearity. And now I have alpha, which is just see if I was. Yes, so it's the next. So then I have alpha, which is a word in this calligraphic A, which are the words in letters of the Ds, and also on the letters of n to the power d plus 1. So these are non-commutative letters. And if you want, if I have a variable of this form, I can compute associated to it an elementary differential, so an analytical object, which would be I select, if you want, my nonlinearity, A, mathfrak, Bourdieu, and then I apply successively some derivatives, and the order will depend on the order of the letters. So, for instance, if I have a letter which is a boldface N, it will be associated to that derivatives. And here it's not EI, sorry, it's a typo. If I have a letter which is DI, it will be associated to this partial derivative XI. So if you want, this word with these order letters will correspond to order derivatives on my nonlinearity. And the order really matter because if I change the order, I don't get the same result. So now if you want, I can consider this multi-indices over this generalized variable where I have L and this word in non-commutative letter that will encode this order and derivatives. So as before, I can define the populated conditions where I have to define the length of the word alpha. And when I compute the length, I don't care about the partial derivative in xi. I just count the letters which are in nd plus 1. So the idea is that if you want this polynomial or this di or dj, they don't count in for these populated conditions. Okay, so that's the notations. And then, yes, there is a question about the coding. Because historically, I mean, if you want, sorry. Yes. So the way of coding this multi-index, it's not originally the way people were using it for SPDs. They were, instead of putting the partial xi, or if you want the derivative, polynomial, I mean, these directional derivatives, they were creating special variables for dealing with these derivatives. So this was, but this is, so this is explained on the slide. You try to put them on the side and to represent them with some variables Zn, where n belongs to nd plus 1. So these are another set of variables. And in fact, our notation is more compact because if I take, for instance, a variable which is a mathfrak L and then a directional a letter di, then I apply my partial derivative on this term, I do a shift, and then if you want this term, encode actually a sum over multi-index. So if you introduce this variable Zn. So in fact, what people did, they actually apply the chain rule, they expand everything, and then they collect all the terms and they associate to them a multi-index. In our case, we don't do that in the sense I don't use the chain rule, I don't apply the chain rule, I just keep the derivatives in place, and this gives me a more concise coding. So that's a different perspective. Okay, so then for when we use this formalism, the derivations are actually quite easy to write because they just correspond to add letters. So for instance, if I have a derivation dn applying to this variable mathfrak L alpha, it just boils down to add one letter to alpha. So I just add one letter to alpha. And here, be careful, the order matters. So that's why I put the letter on the left, and it matters because it says that I put these derivatives after the others. The same for this abstract partial I, which corresponds to the abstract version of these directional derivatives. I will put, sorry, it's here is D, but I will put the letter also on the left. And then one can check that by these definitions, if I try to look at the commutator between these abstract derivatives, the identity you can see here correspond exactly to the identity you get when you analytically you compute the commutators on the derivatives. And as before, you have the same family of products which are defined before. And then you still have the multi-Novikov structures. But you have this extra structure which are these partial I derivatives. And now, because we get a bit more structures, we want to say something about this multi-Novikov really algebra, incorporating this extra data in our structure. Okay, so for doing so, the idea is the following, is that what should be the intuitions? The intuition would be that, of course, if I consider all these words with any order on derivatives, I may not see something very interesting. So in fact, I may choose a specific order. For instance, I may want to have all the d derivatives coming first, like coming first in my word. And then the rest of the letters will be just the d. And if I look at terms like that, okay, then all the d's, they just could be seen as just one variable, okay? So just one part of my word. And the rest of the words, which are all these d's, could be seen as the same as before. So then I can get here, I have the intuition that I can get a free multi-Novikov algebras. But then I have to explain, actually, if my word is not ordered this way, I could apply a procedure, or like these identities here, actually I can flip the letters just to express it in a nice way, just to get this canonical form. So if you want that intuition you can get, or what should be, what type of tree structure you can get on these objects. So, but in the paper with Dotsenko, we also use a different another formalism, which is also acting on these operations. So we look at the notion of extended algebras. So we have, imagine a set A, and this set A is just nd to the power n to the power d plus 1. So that corresponds to all the letters of the alphabet that we considered before. And we suppose that this is an algebra. You have this algebra, P subscript capital A, and then you have a family of operations associated to this algebra. And these operations, for sure, I mean, in our case, that would be this dn. Okay, so these are the operations dn. So then we could linearize version. So we just extend these operations by saying that I can insert, instead of n, I can insert a linear combination of words. So I can extend them by linearity, these operations, to any linear combinations of letters. And we suppose that the vector space, which is the linear span of these letters, you get a representation of a Lie algebra. So in fact, what happened is that this representation of a Lie algebra will be given by this partial I. So like this, you have would given by this derivative partial I. And then you can define the class of G extended this PA algebra, which with this representation, which satisfies this identity with the Lie bracket. And then you have a certain identity. So you apply alpha of G, which is this partial I, and then you can act on the letter V, which is actually on the N by removing EI. So it's what happened when we check these identities, or when you have this identity that you act on the derivation capital D. So this is the actions given by G. And then you act also on all the variables of F of the operator. So if you want, your partial I will eat all the terms, in your in this operator, and also will act on the decorations of the operator. So it's what happened in the identity partial I and try to commute it with the dn. You commute and then you act also on n. So with these actions here, ball n is equal to n split I, ball n minus ei. So that's, if you want, just a generalization of just identity to see this as a level of these operations. Okay, so just generalizations of this. So in fact, what we saw is just a special instance of this general framework, the way we act with these derivatives. Yes, and so what we proved with Dotsenko is that we have some the free G extended PA linear algebra is isomorphic actually to the free algebra generated by W, which is just a linear span vector space generated by the noises actually, or the L minus, and the universal envelope of G of your Lie algebra, which is and so if you want, you can rephrase this theorem as the fact that that the multi-Novikov algebra of populated multi-indices is isomorphic to the free algebra generated by the set n to the power 1 times L minus. So just to tell you that the multi-indices, the SPD multi-indices, the one with this word and so on, they could be freely generated by using the derivatives, and this we have some with by this multi-Novikov algebra. So if you want, that's an equivalent to the tree version. I mean, I would present the equivalent at the level of the trees, but that gives you a way to freely generate all the terms that appear in the expansion of a solution of a singular SPD. Okay. No. Yes. So that's a result that we obtained at the level of free multi-Novikov. And in fact, this result is quite inspiring. Also, that propositions actually show also the case of multi-pretty. So now I would like, for the rest of the talk, explain the connections with the trees. Okay, so now what I will do, I will consider decorated trees. And I will start with planar decorated trees. So here I've used the symbolic notations, but if you want, I will explain it on the trees here. So I have many ages, and they carry decorations, and they are of different type. So if you want this one with this psi, and I have a mathfrak L1, that will be for noise. So that gives you which noise I want to select. Then I will get a decoration here, which is A. A belongs to n to the power d plus 1. And then I could put a noise on top of that. And then I have also terminal ages, which are this xi. So this xi would amount actually to take derivative partial x. They correspond to these directional derivatives. And if you want this a, they correspond to these derivatives of u parentheses to the power parentheses a. And for the moment, I will assume that these trees are non-planar, in the fact that these two trees here, if I try to permute the tree in the center with the tree with the branch on the left, this is a different tree. Why I want to assume that for the moment? Because I may want to see these edges as derivatives acting on some non-linearity. So the derivatives a priori may not commute. So I want to reflect the fact that they would not commute by putting planarity at the first place. And then what happened is that, as before, with my words, I want to quotient these planar trees with some relations that reflect the fact that this derivative partially will commute. So for instance, I want this identity on xi, xj that correspond exactly to the fact that these two letters commute and the fact that the partial directional derivatives commute. Then if I have two planted trees with a plant which is decorated by A and B, they also commute. So that's also perfectly in agreement with the fact that the derivatives commute for these with the variables u. And now I have the identity, which is non-trivial, the fact that these two derivatives do not commute. In the fact I'm able to permute, if you want, the edges, but I create some correction terms, a tree where I have removed one edge of the xi have disappeared, and I just have to remove one decorations on one edge. So if you want, this is trees which are planar. I quotient them with some relations, which are exactly the relations that comes from these derivatives. And now I want to define a pretty product on these trees. Which is here. So in order to define the multi-pretty or the pretty structures, I will use a product which is left grafting. So I graft that tree, if you want, with on the leftmost locations. So by leftmost location, that I can put the noise is inert, so I can put it here on the center. So yeah, this is yes, on the leftmost locations. I put it here. And then because of the relations, I can permute these two edges. So I have that term plus a correction term where I have to subtract EI to A. So if you want that tree, it's actually equal to this term. So if I use this quotient, I use this left grafting, which is not very difficult to show that it is actually a pretty product. And actually, you have a free structure also for this pre-product. So it's also a free 3D product on these trees. And in fact, you have an equivalent of the theorem for Novikov, is that the multi-pretty algebra generated by these trees where you do the quotient and this left grafting is actually isomorphic to the free pretty algebra generated by all these elements. So I keep the noise and I keep x to the power k, meaning that I put all the xi first. So for instance, in this, if you want, this element will be in the basis. So I have all the xi first. So when I graft, then I have to permute my new age with all the xi that produce many terms in order to write them in the correct basis. So this theorem was known for a while, I think for SPDs, we proved it in 17. The paper has been published in 21, but this has been proved, was known for a while for these decorated trees with this left grafting. So what we did actually was to extend this theorem and to see it as a Novikov level for multi-indices. And then, of course, you have a map and a pretty morphism that sends these trees or these decorated trees to the multi-indices that I introduced. And the fact that you see the quotient on the tree reflects the fact that you have a quotient at the level of the letters for the multi-indices. So now I will conclude my talk with some remarks and perspectives. Is that knowing the fact that where we were working with decorated trees, knowing the fact that it is pretty actually gives you a lot of nice properties and also applications. Now we know very recently that multi-indices, which are natural expansions in dimension 1 for SPDs, also for ODs, are free Novikov. So maybe we can take advantage of that. In fact, that I think there is an abundant literature on Novikov. This can give us more interesting properties that could be used in this context for these expansions. Also give a way to define uniquely Novikov map, or if you want free Novikov morphism for your trees or for your applications. So that's a nice application. So that could be, for instance, for renormalization maps, because we define renormalization maps uniquely as 3D morphism for the trees. There is a more general question, which is open, but for that, I believe that maybe the answer is quite pessimistic, but the idea would be maybe there could be other structures apart multi-indices and trees for dealing with this expansion of solutions. But maybe at the pure algebra level, you can find a nice structure in between, but to reflect that these are clearly the kernel of some elementary differentials, it seems, or at least that for the moment, we know only multi-indices and decorated trees to be useful. Also, what I presented here was so this fact that these derivatives do not commute you have a way to you have behind the scene you have some post-Lie algebras that come from this Lie algebra. And so then all this Novikov algebra could connect to this post-Lie algebra, or if there are some links or not, and also some deformation theory. And also what I say that, for instance, in multi-3D, it's 3D, you have a nice geometric interpretation. Also in Novikov, maybe you have some geometric interpretations that could maybe give some insights on these expansions. So yes, so I will just think I conclude on these remarks, and thank you for your attention.
Thank you very much, Yvain, for this very nice talk. So do you have questions or remarks, please?
Yeah,
okay.
there is
may I have other question? Sorry.
Yeah.
Okay.
Yeah, this is Li Guo.
Yeah. Hi, Li.
Okay.
Please
Hi,
ask.
Dominique. Yeah. So yeah, thanks for the very nice talk. So just for our perspective, right? So the multi-indices. Can we just look at it as the free commutative unitary semigroups or monoids, right? So with those generators, and then the indices are the powers.
Yes, so you mean that, for instance, if you look at this one
Yeah,
form,
if I can still see the slides, yeah,
yes,
somehow it disappeared.
Yes.
Right. So at first you have a sequence of generators, right? So then as you said, looks like that there are infinite variables, but only finite many have positive indices. So that's like how you express free commutative monoid or unitary semigroup, and then you just collect the one with positive powers. And
Yes.
then if you have multi-indices, I mean, if you have more variables, then you just increase the generator set, right?
Yes.
And make your set very big. Yeah. And further, maybe you are aware of this already. So there is a branch of algebra called differential algebra. So for differential algebra, it works with commutative rings with derivations. There could be multiple derivations.
Yeah.
And then for those objects, if you look at the free ones, right, for any algebraic structure, you look at free objects first, as you do in your paper with Dotsenko. So and there, if you want to construct free differential algebra with certain set of derivations, then construction would be there are polynomials with variables consisting of these differential variables.
Yes.
Yeah. So that might help to see the meaning of multi-indices. Okay. Yeah, that's it. Yeah.
In fact, the choice of the variables here, they reflect some derivatives, analytical derivatives. The same that started with ZK, which were the index set for the variables was just n. That corresponds to a certain number of derivatives that you apply on F. And then enlarge the set by taking a more complicated set. First, monoid on a commutative monoid on nd to the power 1. And then I have to introduce other letters that do not commute because I have some derivatives that do not commute. Then you could think about more complicated sets for indexing this Z. But the one that I've chosen were purely motivated from the analysis.
Right. Yeah. Okay. Yeah, it's the same as differential algebra, which also, as the name suggests, come from analysis, differential equations. Yeah. Okay.
For instance, there are like the proposition we studied with Dotsenko, the one for proving the last theorem, where you have some operators and you act on these operators. That's a very general statement. I mean, in the sense that the two instances of applications are these multi-indices and the trees. But you could think about, I mean, this is very abstract. You could think about other operations and having this, for instance, what we did here. Yes, this formalism. That's a more abstract formalism that allows us to encompasses or to cover what we need, but it's a bit more abstract than just actually the applications.
Okay.
Okay.
All right. Thank you. Yeah.
Thank you very much, Lee. Are there other questions or remarks?
There was a remark in the chat saying that you can call it also Gelfand-Dorfman Novikov algebra, so we could add also more. There were people saying that it was also coming back from Gelfand and Dorfman in 1979, and it was discovered in Novikov and Ivanisky. Yeah, you have some remarks on the historical origin of Novikov.
Yeah, in fact, in this 79 article, Gelfand and Dorfman just look at an associative algebra A derivation on A, and they cook up a product, A triangle B is equal to A multiplied by DB. And they notice that they fulfill what is called now the Novikov axioms. But the name Novikov algebra was not formalized yet. And, so this is the first example due to Gelfand and Dorfman. So are there other questions? So because if not, I do have a comment on the last slide about the perspectives.
Yes.
You asked the question whether the free Novikov algebra is free as a Lie algebra, right?
Yes.
The answer is definitely no. This is in sharp contrast with the free pre-Lie algebra. And the supplementary relation is quite easy to find. So if I'm not mistaken, you look in the free pre-Lie algebra, you look at ladders of size 2, 3, 4, and 5. You do the bracket, the Lie bracket of the second with the fifth, and then the Lie bracket of the third with the fourth, and you cook up 1 time the first term minus 3 times the second term. And then you apply the fertility map to this. That means that you project this element on the free Novikov and you get 0. It's an easy exercise. It's very nice to check, and then you have obviously found a supplementary relation on the Lie algebra of multi-indices. So definitely it cannot be free. Okay. Yeah.
I didn't know such a easy counterexample.
Yeah, but
I discussed that with various people, and they are clearly
I cannot believe somebody didn't write it before, but I didn't find, so it's nice to know. Yeah.
Good to know.
Yeah.
No, yes, this last slide is more about the fact that I'm not an expert on Novikov algebras. I know there are a bunch of properties or maybe a bunch of applications you can do with them. Is that now they appear naturally in the context of ODE and SPDs. And these have been extensively used in the sense that you have a big literature right now of strong paper and SPDs who are using these multi-indices. So if people have applications on Novikov, algebraic properties that could be maybe transposable on the analytical side, maybe that's a dream. But knowing that, I mean, can help us maybe finding other nice analytical relations or nice identities that we missed when we do these expansions with multi-indices. So that's my aim for exploring these structures, to get more knowledge of the object, of the expansions that I'm doing when I'm solving singular SPDs.
Okay. So if you don't have any other question or remark? Or if,
Yeah, could you turn to page 9? Page 9.
yeah. Xing, yeah. Yeah, page 9, yes, okay.
Page 9.
Yes,
Can you...
we can go page 9.
Yeah.
Yes.
Here, define the size of alpha. Why you define
Yes.
What?
in this way? You don't care the partial. Why the size of alpha defined in this way?
The sum here, for the populated SPDs or populated multi-indices.
Yeah, but here the size of alpha, you just count the number of letter n.
Yeah, so yes, it counts the number of letters, but of certain specific letters. So if you have the letters which correspond to this partial derivative in xi, which are this di, you don't count them, you just count the n.
Why you don't count the di?
Yeah, you don't count these letters. So if I show you, I don't count these letters. So why? Because when I do an expansions, if I put an xi, then my expansion is over. In the sense, the terminal edges. Or if you want, I will not continue the expansion further. But if I have a u, then I can continue to expand. So if you want, because if you think of multi-indices, these are blocks with entries that correspond to the, for instance, zk has k entry and one outgoing edges. And then you can try to build up trees out of these blocks. So then the idea is to say that when I build up trees out of these multi-indices, the one which are the letters which are decorated by nd to the power 1 will be edges they're decorated by nd to the power 1. So then I can put multi-indices on top of the order. But the xi that correspond to this di, this will be edges which are terminal edges. They lead directly to a leaf. So I cannot put something on top. So that's why I cannot count them in the populated conditions. So for instance, if I go back to the trees here. So these edges, xi, which correspond to the letter di, it is the terminal edges. It corresponds directly to a leaf. So I cannot put on top of that a node. I mean, this is forbidden. So that's the reason that you have to disregard them in the populated conditions. They don't play any role.
Okay, thank you.
Other questions? Okay, if not, I suggest to thank Yvain again. Thank you very much.
Thank you.
Thank you. I'll be here.
Okay, so Jobir, you want to add something to conclude?
No, we can stop if.
Okay, so let's stop here and thank you very much, everybody.
Okay.
Bye.
Goodbye.
Goodbye. Thank you.
Bye.